My name is Anuradha Karupia. I'm an engineer at NVIDIA. Today, I'm going to take you through the life of flooded traffic, bomb traffic, broadcast, unknown unicast, multicast traffic in a EVPN network with multi-homing. The reference topology that I'm going to use for this discussion is a two-level class. It has two racks in it, rack 1 and rack 2, with two top of rack switches per rack. These top of rack switches are at the L2 L3 boundary. They are EVPN PEs and function as VTIPs to extend the broadcast domain from rack 1 to rack 2. The servers on the racks, host 11 and host 21, are multi-home to the top of rack switches. We're going to look at bridge traffic within VLAN 100. VLAN 100 is extended using VNI 10100. The traffic we're considering here is bomb traffic. So let's take an example. Let's say host 11 sends an ARP request for host 21. This is a broadcast packet. When TOR 11 receives this packet, it's expected to flood it to all the VTIPs that are participating in this VNI 10100. To do that, it uses PIM-SM in the underlay. So let's first look at how the multicast distribution tree is set up. The rendezvous point is set up here in this example on the spine layer. It's an anycast rendezvous point 100.0.0.1. The VNI 10100 is mapped to a multicast replication group 239.1.100 for the purpose of flooded traffic replication. The VTIPs that are participating in VNI 10100 join the rendezvous point tree 239.1.100, and this happens ahead of time before any traffic is received. Similarly, all of the VTIPs register themselves as sources for that multicast group, and that is done via null register messages. This priming of the pump allows for lossless traffic forwarding. Now that the multicast distribution tree has been set up, let's take a look at what happens when the broadcast traffic is received on TOR 11. When TOR 11 receives this traffic, it knows that VNI 10100 is mapped to multicast group 239.1.100. So VXLAN encapsulates the packet using DIP 239.1.100 and forwards the encapsulated traffic using the multicast distribution tree that has already been set up. So all of the VTIPs that are participating in VNI 10100 are going to receive a copy, encapsulated copy of the packet. These VTIPs, left to their own devices, are going to decapsulate the traffic and send it down to the servers. So TOR 21 is going to send a copy to host 21. Similarly, TOR 22 is going to send another copy to host 21. Likewise, TOR 12, which is in the rack for originating rack 1, is going to send a copy back to the source, host 11. Clearly, we have a problem on our hands. Host 21 is receiving duplicate copies of the bomb traffic. Host 11 is receiving a copy of its own traffic. How is this solved? It's solved using designated forwarder election. A preference-based DF election mechanism is used for Ethernet segment. This is via the Type 4 EVPN route, the Ethernet segment route. A DF preference can be configured per Ethernet segment on each top of rack switch, and the top of rack switch with the highest DF preference on an Ethernet segment wins the DF election. So in this example, TOR 12 wins the DF election on Ethernet segment 11. TOR 11 is the non-DF, and the non-DF is expected to drop egress bomb traffic on Ethernet segment 11. Only the designated forwarder is allowed to forward traffic, bomb traffic, post-decapsulation. Similarly, on rack 2, TOR 22 has won the DF election, and TOR 21 is expected to drop egress bomb on Ethernet segment 21. Let's put the misbehaving bomb traffic back and see how things play out with DF filtering. If you remember, TOR 12 won the DF election on Ethernet segment 11, and TOR 22 won the DF election on Ethernet segment 2. This means that TOR 21 and TOR 11 cannot forward the decapsulated traffic. So TOR 21 has stopped sending the traffic down, and only TOR 22 is sending a copy to host 21. So the problem has been solved on rack 2. Host 21 is receiving a single copy of the bomb traffic from host 11. But what's going on rack 1? TOR 12 is still sending a copy down to host 11, so host 11 is receiving a copy of its own packets. TOR 12 is doing the right thing here. It is the designated forwarder after all. So how is this problem solved? It is solved using split horizon filtering. To understand split horizon filtering, let's take a closer look at traffic within a single rack. This is a pattern version of the same topology showing just rack 1. There are two servers on the rack, host 11 and host 12, and we're going to look at flooded traffic from host 11 to host 12 via VLAN 100. TOR 12 has won the designated forward election for Ethernet segment 11 and for Ethernet segment 12. When broadcast traffic arrives from host 11 to TOR 11, TOR 11 is going to flood the traffic out of all the access ports in VLAN 100. This includes BON 12. That's Ethernet segment 12. So host 12 is going to receive a copy of that BOM traffic directly, that is access to access. This path is the preferred path, and that's called local bias. In addition to this access-to-access flooding, TOR 11 is expected to send that traffic via the VXLAN overlay to all the VTIPs participating in VNI 10100. That includes TOR 12. So TOR 12 is going to receive an encapsulated copy of the same BOM flow. TOR 12 decapsulates the traffic and sends it down ES11 and ES12 as it is the designated forwarder. So we have the same problem again. Host 12 has duplicate copies coming in, and host 11 is receiving a copy of its own packets. If you recall, there is an ES mapping table that is maintained on each EVPN PE. This mapping table is populated using the type 1 EVPN route, Ethernet auto discovery route. This ES mapping table enables each PE to know about the Ethernet segment pairs that are attached to the same Ethernet segment. So TOR 12 knows that ES11 and ES12 are attached to TOR 11. It uses this information to set up the split horizon filter. Split horizon filter prevents traffic coming in from an Ethernet segment pair, encapsulated traffic coming in from an Ethernet segment pair, being sent back to the same Ethernet segment post-decapsulation. So on TOR 12, you have a split horizon filter to prevent traffic coming in from TOR 11 heading back towards ES11. You'll have another filter to prevent VXLAN encapsulated traffic from TOR 11 going out of ES12. The first split horizon filter prevents traffic from TOR 12 to host 11. So the first problem is solved. Host 11 is no longer receiving a copy of its own packets. Because of the second filter, TOR 12 stops sending traffic towards host 12 post-decapsulation. This is traffic from TOR 11. Because of this filter, host 12 stops receiving duplicate copies. So now we just have a single copy going from host 11 to host 12. This is local bias with split horizon filtering.
That's flooded traffic within a rack and from one rack to another rack, optimized using PIM-SM in the underlay. In the next episode, we're going to examine something that is very hard of EVPN multi-homing, efficient failovers.